This lesson, we're going to just look at some examples of integrals and decide if you can use U substitution. So if we're looking at this first one, you might think, okay, so the inside function is this one. And if that was the case, you would need its derivative somewhere in the problem, and you don't have that. And then you might say, okay, x is the inside function, which it never will be because you wouldn't need to do U substitution for x being the inside function. So this one is no. We can't, even if you wanted to, you cannot do U substitution here. All right. And then when you look at B, same thing. Like we have this fraction. So then you're like, okay, the denominator is the inside, and then but then you have all this x, 3x squared. So this one is also no. Okay. And then same thing for this one. We could say u is this denominator, but what is all this stuff? So this one would be no. And then same thing on the last one. So none of these can be integrated using U substitution. So what we're going to do instead is simplify the radical. All right. And so what we would want to do on the very first one is go ahead and rewrite it as the quantity x squared minus 4x times x to the 1/2 dx. And then to simplify it, we would distribute x to the 1/2, which means we would add the exponents 1/2 and 2, and we would get x to the 5/2. And then for 4x times that, we would add the exponents 1/2 and 1, and we would get 3/2. All right. And then this one, we would just start to integrate just using the power rule for integration. So we would add 1 to our exponent. So that first one would make it 7/2. And divide by our new exponent or multiply by the reciprocal. Okay. And same thing on the second one. We would add 1 to our exponent. So that's going to be 5/2. And divide by that or multiply by the reciprocal. And then we have plus c. On a free response test, just leave it like that. Multiple choice, most likely, it would be they would multiply 4 times the 2/5 and get the negative 8/5. But like I said, free response, you just stop right there and you're done. All right, let's look at the next one. We already said no, we cannot do U substitution. So what we're going to do is going to be way easier. We're just going to go ahead and divide 3 by x. All right. And then we'll just take the integral of each term or find the antiderivative of each term. So this is adding 1 to the exponent, dividing by the new exponent. The integral of negative 4 dx is going to be just negative 4x. And then for 1 over x, the antiderivative of that is the natural log of the absolute value of x. And then because this is an indefinite integral, don't forget the plus c at the end. Okay. Now this one, we can't do like what we just did where we just divided everything by x. this one, we're going to have to either do long division or synthetic division. So I don't know how much of that you guys remember, but as long as this, what you're dividing by is linear, so it doesn't have a power and it doesn't have a coefficient, then we're going to do synthetic division. All right. And so to set it up, you do the box. Whatever this is, you do the opposite of it in the box. And then you bring over your coefficients and your constant of the dividend. Now, if something was skipped, like if it went from just x cubed to x, we would make sure we fill in a 0 there, but it didn't. We didn't have to on this one. All right, so then we bring down the first term, and then from here on out, it's multiply, add, multiply, add. So you multiply the number in the box by the number under the line, and then you add these two together. And then you do it again, multiply the number in the box by the number under the line, and then you add. And then one more time, you multiply, and then you add, right? And so now we can write a brand new integral that we can integrate pretty easily. So we started off with this x cubed and we divided it by x. So this means 1x squared minus 5x from this 5 plus 1. And then we always do our remainder over the divisor. So now I can just integrate each term. So the first few terms, we're just doing the power rule for integration. Right. Now when we get to this one, it's a little bit sketchy. We have to be careful. We can actually kind of skip over the U substitution on this one. So let me write this down. As long as you have a number over a linear expression, as long as that derivative of the linear expression is 1, we can kind of forego the or skip over, just omit the U substitution. So I'm just going to make a little note over here. So we have a number over linear expression. So you can I feel like I'm spelling this wrong. I feel like there should be an E in it. Forego U substitution if the derivative of denominator is 1. All right. So then when I go to find the derivative of 4 over x plus 3, I can kind of treat it like it was 4 over x. So it's going to be 4 and then the natural log of x plus 3. And then you just add a plus c. Now, if we had done U substitution, it would all work out the same way. It just would have taken a lot more steps. So as long as like your inside, what you consider your inside term, has a derivative of 1, you don't really have to do U substitution. You can just put the x plus 3 where you would normally have put the x. Okay, let's look at the next one. All right, so So this one was also a no. And we can't divide using synthetic division, and we can't divide like we did on B. We're going to have to do long division. All right, so we take our divisor and put it outside that like division box thing, and our dividend under. And then as you're dividing, you're really only focusing on the first terms. So you ask yourself, what do you multiply x squared by to get x squared? And that's just 1. So I normally kind of line up my like terms, or like if I put my constant over my constant. And so then I would distribute that 1, and you absolutely have to line up your like terms at this point. So you'd write x squared under x squared, constant under constant, and then you are going to subtract. So we're going to subtract both of those. They subtract away, but this x becomes our remainder. So that is the answer to that division problem, which makes that also be our new integrands. Okay. So on this one, because it's kind of weird, like it's a little more complex than the other ones we were doing where we had multiple terms, I'm going to actually divide this into multiple integrals. Okay. Now before I was talking about like we had this situation where it was a number over linear. We could just kind of skip over and not do U substitution. This is not one of those cases. So on this one, we're going to have to do U substitution. So I know at the beginning I was like, you can't, but once we divided, now it's set up in a situation where we're going to do U substitution, where U is going to be x squared plus 1. The derivative of that is 2x. So du is 2x dx. All right, so I'm going to wait and do both of these integrals at the same time, just so things don't get too confusing. If you want to go ahead and do that first one, it's fine, but I'm going to wait. So I do have to correct this integral because I need a 2x, and I only have an x. So I'm going to do a 2 here, a 1/2 there. Okay, and then I'm going to rewrite it again for all you people out there that want to see it that way. All right, so now I will still hold off on this integral of 1 dx. Okay, so I'm going to do my U substitution part where in the place of x squared plus 1, I'm just going to call that U. And in the place of 2x dx, I'm just going to call that du. All right, I'm ready. I'm ready to do my integral. So the integral of 1 dx is going to be x. And that 1/2 is going to hang out. And then the integral of 1 over u is going to be the natural log of the absolute value of u plus c. All right, and then I'm going to stick in what u is. And I just realized that we are not going to end up needing those absolute value bars, because x squared plus 1 is never going to be negative. If you square a number, you're going to get a positive. You add 1 to it, it's going to be positive. So you technically don't need those absolute value bars there at the end. You can leave them as just parentheses. All right, So that is using division to simplify your integrand, and the first one was using multiplication to simplify the integrand. Right. The other thing that I want to talk about today is using geometry. Now, we use geometry a ton to find integrals. All those Riemann sums and trapezoidal sums was using geometry. This is going to be slightly different. We're going to need to know what these graphs look like, and then we can use geometry to find the areas. So this is one that you may not be super familiar with, but I think you might be familiar with this. I hope so. The x squared plus y squared equals 9. That is a circle. And this is a circle that is centered at the origin, and the radius is 9. Oh, just kidding. The radius is 3, the square root of 9. All right, so if I took that and I solved it for y, and then took the square root. Now, if you look at this one, it's only the positive square root. Typically, when we're solving for y, we would do plus or minus, but if we're wanting it to be a function of y, we would only do the positive square root. And so that's the top part of the circle. So this is a semicircle. Okay, so hopefully next time you see that, you might recognize that that's going to be a graph of a semicircle. The radius is going to be 3, and it is going to be the top half of the circle. That's not a great circle. It's close though. All right, and so we're wanting the integral from 0 to 3, so it's going to be this section right here. And so that technically is a quarter of a circle, so it's going to be a quarter of pi r cubed. R is 3, and so that's going to be 9/4 pi. Is going to be the value of that integral. Okay, and then for b, right, this is another one. We're doing all of these using geometry, so we're going to need to know the graphs of all of these. And so we want the sine curve from negative pi to pi. Okay. And so what happens on this is it does this number, right? And it does keep going, keeps repeating that pattern. And so the area that is the value for this integral are those, like, we would subtract this bottom one and add this top one. But the way the sine curve is set up is that it's going to be symmetric. So anytime on sine, if you're going from a negative number, it could be negative 500 to 500, that bottom area is going to always match up with the top area, and it's going to equal 0 when you add and subtract it all together. That's a little shortcut for you. All right, and then this last one, you're going to need to remember what an absolute value graph looks like. So an absolute value graph is a V graph. This is a V graph that has been shifted 5 units to the right. Okay, and so I haven't drawn these super symmetrical. It's kind of all over the place. But anyway, this basically is what the graph looks like. We are wanting the integral from 2 to 8. So this is 2, this is 8. So it is going to be these areas added together. And so the slopes of these sides of this V graph is basically this side is -1, this side is +1. And so for this triangle, this is 3, but this is also 3. And so we would do 1/2 base times height. And the same thing here. This distance here is 3, this one is 3. So it is also 1/2 base times height. So those are both 9 halves. They're both above the x-axis, so we're adding them. So that's 18 halves or just 9. All right. So your assignment for this lesson is to do this worksheet where I have told you what method I want you to use. So this first one's using the antiderivative rules. They're not all basic. Some of them you're probably going to have to look up, like especially this one. And then simplifying the integrand, so doing division, doing multiplication, whatever you need to do. Use substitution. This one, this one right here, if you use a rule for what cosine of x or sine of x is, you can, and then you go back and you look at this, you could do it. It's just making sure you have that memorized in the long run. And then the last 3, I want you to use geometry to do them. And then tomorrow we'll practice on you deciding what method would be